In this example, we're going to examine a game of roulette. We're told some things about the game itself, like it has 38 slots, and to play a metal ball spun around the wheel, and it falls into one of those numbered slots. If the number on the slot of the ball falls into and it matches the number you selected, you win $35. Otherwise, you lose $1. So the first part of this problem asks us to construct a probability distribution of the winnings. In other words, what's the probability that you will win $35? Now, I've already typed this in here as a decimal, but I got that decimal just by dividing 1 divided by 38, because there's one way to win out of 38 possibilities. There are 37 ways to lose out of 38 possibilities. So that's where these numbers come from in our probability distribution. Next, to determine the mean and standard deviation, I'm going to go to the list, and I'm going to type in this probability distribution. And I'm going to use the values that I rounded to here in my math lab. Otherwise, I probably would just have typed the fractions. All right, from there, I'm going to go back to Stat, Calc, and I want to do 1var stats. Treat this one like a list with a frequency list. So we have the list of outcomes in list 1, and their frequencies are the probabilities in list 2. We'll calculate. Notice here's the mean up here at the top, and it's the negative 0.05 when we think about this in terms of money. So we're looking at there a mean of losing 5 cents. The standard deviation is here, 5.76. So then we're asked some questions about different sample sizes, essentially. Let's say we play the game 70 times. I think later it asks 140 times and then 700 times. So let's go through how do we calculate these different probabilities with these different sample sizes. First off, we can assume here that the sample mean of X bar is approximately normal, where the mean of the sampling distribution of the sample means is the same as the population, but the standard deviation, remember, is different. So we will do 5.76 divided by the sample size, divided by the square root of the sample size. Here that's 70. And that's how we obtain this standard deviation, which when rounded to the nearest penny is 0.69. Next, we're asked to find some probabilities related to this particular sample size. So here is where we would turn to the distribution menu, normal CDF. We want to know the probability that the sample mean is greater than 0 for n equals 70. So the lower bound is 0. Upper bound, we'll leave at the highest value. The mean we just determined and the standard deviation we just determined, they're over here. And that's how we get the probability that the sample means are greater than 0 if the sample size is 70. In other words, think of it like the probability that you're ahead. You're at least above 0 in the positive. Okay, about 47%. Now, as you increase the number of games played, let's see what happens. So let's look at these two particular sample sizes. Everything else stays the same except for standard deviation. And actually, what I'm going to do here is I'm going to go back and grab that original population standard deviation and divide by the square root of the sample size. And I'm just going to leave it like that in my calculator right here. So that original population standard deviation divided by the square root of 140. This is for part E. Okay, so we get this probability, 0.4591. Now when I go back and do that again for a sample size of 700, let's say you're playing 700 times, a little bit smaller, 0.4092. So what happens? What does this teach us? It teaches us that as we increase that number of times played, our probability of being ahead decreases. And we can see all the different options here. But if you think back to expected value, that should hopefully make a little bit of sense as well, because we're increasing this in this sample size.